Okay, so here's another kind of situation that deals with the diffraction grating. If you have two slits, we'll get interference fringes that maybe look like this. If I increase this from 2 slits to say 3 and give them all the same distance between them, I get this pattern. And if I increase this to something like 10 slits, or why don't we just go up to n slits, a lot of slits, we get a pattern that looks like this. So in this pattern, what is the take-home message? The more slits you have, the more focused or the more contained each of these fringes. But what can we say about their locations? They're all the same. If you want to deal with a diffraction grating, d sine theta equals m lambda, and this predicts your bright spots. It's exactly the same as 2-slit interference. It's the exact same phenomenon. The only difference is the width of these are much more collimated, focused to a single point. A warning. Typically, not always, but typically, diffraction gratings usually have a lot of slits really compact and close together. So Ds are usually pretty small. The smaller the D, the wider the angle to satisfy this equation. So we tend to notice with diffraction gratings out in the world, they end up having their fringes spread out a lot. So much that maybe the small angle approximation is not appropriate. So if that's you and that's your situation, typically not small angles. You should always just go back and just double check this, right? Just see, does this work or does it not work? Then we also have interesting patterns. I think you'll do those in the lab, right? We can have slits that, fine, here's your grating that gives you something like that. But we can also complicate it and make it 2D. So then our diffraction grid pattern might be kind of spread out and look like a 2D array. So these are just things that you should know about. Okay.